So, talking about complex skills that people typically learn by being taught to do it, programming is one of the kind of canonical ones, right? That, we teach a lot of people to program at MIT, and of course the main way in which we do that is we bring them into a classroom, we give them lectures, and then we give them assignments, and we give them books to read and work to do on their own. And so one thing that my group has been working on in collaboration with Josh Tannenbaum and his group in Brain and Cognitive Science is building machine learning models that can generate code as well. And in particular that, given some example inputs and outputs that you want your program to produce, learning to automatically generate programs that can transform all of your inputs into your outputs. One sort of simple example of this that people may have actually seen before is in Excel, right, where if you sort of enter a pattern in the first couple of cells and then you ask them, the spreadsheet to complete the pattern, often it can do that in fairly complicated ways. And in fact, what's going on under the hood is that it's inferring a little computer program, a little Excel formula that describes all of the entries that you've produced so far and figures out how to generalize them to new cells. And we want to be able to do that at a much larger scale, not just with like little words and numbers, but basically any kind of input-output mapping that can be expressed as a program. This turns out to be a very difficult problem to do on its own because basically a machine learning model doesn't have that much structure in these problems to latch onto, right? You see some inputs, you see some outputs, there's just a truly enormous space of possible programs that could get you from your inputs to your outputs, and it's not clear when you start learning how to even begin to search in this space. And so thinking again about the way in which we teach people to program, we sort of give them hints, right? We say, well, here are high-level abstractions, high-level programming concepts that are useful for you in your learning and that you might want to use in the context, when we give people individual homework problems, we give them hints about these homework problems. We say these are, solutions that you might want to consider without giving them the full solution. And it turns out that we can do the same thing for machine learning models that write code as well, that we can give them hints in natural language about how to solve specific problems. We can give them high-level advice about the kinds of program constructs that are useful to use or the kinds of programming ideas that are useful to use. And if you do this, and if you do just very small amounts of this, like an order of 100 hints for a big data set of programs that you're trying to learn, that turns out to be enough to dramatically improve the quality of the best program synthesis engines that we can build. And we can build ones that can solve, for some data sets, like twice as many problems as were previously accessible, just using like a little bit of natural language guidance. So, I think the hope here is that, I don't think we're ever going to live in a world where we're not building models that at some point learn from large numbers of labeled examples. But I think the moral of the story here is that, if you have those labeled examples, adding to them even just a small amount of rich supervision in the form of natural language can really let you squeeze a lot more out of the data that you already have, because it's very easy for people to come in and just write a little text that identifies the important pieces of a data set, the important sort of concepts that models need to learn, and just that little bit of guidance can be quite useful.